Well, good day, ladies and gentlemen. We're off to our next phase of our Chapter 11 adventure. This is actually take 3 of my video trying to complete this section. First time my alarm reminding me to take the garbage out went off and stopped my recording. The second time, I got my notes out of order and my book fell off my desk. So I'm hoping that the old saying, third time is a charm, is going to work out this time. All right, so section 2, measuring simple harmonic motion. Now we got our first introduction to simple harmonic motion in section 1, along with Hooke's law, where we investigated and calculated a mass spring system and its elastic force in conjunction with the spring constant and the displacement of the mass. Here in this section, we're going to be looking at simple harmonic motion in pendulums as well as a mass spring system. So in this section, we are going to identify the amplitude of vibration, recognize the relationship between period and frequency. Now, period and frequency are not new terms to us. Hopefully, we all remember what they mean. If not, you're in luck because we're going to see exactly what those mean again. And lastly, we're going to calculate the period and frequency of an object vibrating with simple harmonic motion. Now, the assignments associated with this section, they're going to come in 2 parts. The first part's going to be talking and discussing pendulum and calculating pendulum. And the second section, which we'll see in our next posting, will be for a mass spring system. So you're going to be getting 2 assignments just at different times for this section. Everything's going to be included in this one video. That way I don't have to sit there and make another video and have it take over an hour to upload. So we get the whole shebang right here. All right. So let's investigate our first objective: amplitude, period, and frequency in SHM, or if you don't like shortening words, that is simple harmonic motion. So in simple harmonic motion, the maximum displacement from equilibrium is defined as the amplitude of vibration. So we're going to be looking at how pendulums and mass spring systems define amplitude. For a pendulum, the amplitude can be measured by the angle between the pendulum's equilibrium position and its maximum displacement. And for a mass spring system, the amplitude is the maximum amount the spring is stretched or compressed from its equilibrium position. Now, we saw that idea of compressing and stretching springs in section 1, so that should be nothing new either. Now, when we are measuring amplitude in these systems, they typically are measured in the units of radians and meters, or I should say and/or meters. Now, we do not use radians in our calculations in this book, so we are going to stick with the good old-fashioned meter. Now again, for those of you who remember what period and frequency are and how they're related, you can fast forward a little bit. But if you just want a nice refresher, or if you totally forgot, stay with me here. The period, as we denote with a capital T, is the time that it takes to complete a cycle. And the SI unit for a period is the second. Frequency is the number of cycles or vibrations per unit of time. How many full periods can be done in a given amount of time? We measure this, or we report this in hertz, okay? Hertz can also be listed or labeled as s to the minus 1, and we'll see why that can be done so in just a short second. The reason why we can list it as s to the minus 1 for hertz, meaning that means per second, that's because period and frequency are inversely related. Okay, so if at any time you know the value for period or frequency, you can take the inverse or the reciprocal of what you know to calculate the value for another. So you really don't have to go through all the other steps trying to get a calculation. Just simply take the reciprocal of what you find, and that's what will give you the other amount. Now, unfortunately, we're not in class, so the pendulum demo is going to have to wait for another year. All right, table 2 gives us a quick rundown of some measures, and it's a nice little reminder of some things that we're looking for and how things are measured. For amplitude, definition, maximum displacement from the equilibrium. It's measured in radians or meter. We're going to be sticking with meter. The period, denoted by capital T, the time it takes to complete a full cycle, it's measured in seconds. And lastly, frequency, the number of cycles or vibrations per unit of time, measured in hertz, or s to the minus 1 per second, okay? Now, we're going to be seeing two formulas in this section. The first one's going to be for the simple harmonic motion of a pendulum, and the second is going to be the simple harmonic motion of a mass spring system. All right. When we are calculating, or the formulas that we're going to be using are all going to be solving for the period of either the pendulum or the mass spring system. For a period of a simple pendulum, it's going to depend on the length as well as the free fall acceleration. So we get the formula of t, or period, is equal to 2 pi times the square root of length divided by the acceleration due to gravity. Okay. Now, in simple pendulums, the period does not depend on the mass of the bob or the amplitude, as long as we're dealing with small angles, that is. Okay, so we don't have to worry about, well, if we have these two pendulums, same length, different masses on the end of it, don't worry about it, okay? That does not factor in. What we're going to be doing towards the end of our lesson here is looking at the calculation of a period of a mass spring system in simple harmonic motion. Again, the period of an ideal mass spring system. Now, that word ideal keeps people out of trouble. They said, as long as everything's perfect, this is how it's going to work. But we know that not everything is ideal. We are going to be dependent on the mass and the spring constant. Those look familiar, maybe from section 1 in Hooke's law. Okay. For the mass spring system, the period does not depend on the amplitude, and this equation for the mass spring system only applies for systems in which they obey Hooke's laws. That is important, okay? All right, so let's take a look at sample exercise B, okay? This is what your first assignment is going to be covering. Your next assignment will be over sample problem C. So let's get started at sample exercise B. So find yourself, and I know you do this all the time, you are wandering just aimlessly. It's been a gorgeous day. You decide it's going to be great to go outside. But you happen to notice that there is a mysterious tower along your walk, and you say, you know what, I had so much fun in my physics class with Mr. Dorfler this year that I want to take things that we took in class and apply them to real life. So you decide, it would be really good to know the height of this tower. But I've been walking for so long that darkness is upon us and I cannot see the ceiling. But thankfully, for some reason, you decide, hey, I'm going to go inside. Well, inside, someone has conveniently placed a pendulum that appears to reach from the very tippy top of that tower all the way to just a fraction of a hair from the very bottom floor, which is great because now we know that we can use the equation to find the period. Okay, so you decide that I can find the period of this pendulum if I take it for a quick swing, and then I can do a little bit of algebraic rearranging of that formula to help me solve for the length, which in turn would help us solve for the height of the tower. So you swing the pendulum. Yes, of course, it obeys simple harmonic motion. And you find that in order to complete one full cycle, it takes 12 seconds. So now that you know that, and of course, we're just going to use the general form of acceleration due to gravity, we can figure out the tower. So we know 12 seconds for a period, 9.81 meters per second squared for acceleration due to gravity. We're going to find L. So we have our formula here. We are going to have to rearrange and solve for L. So first thing we're going to do is let's just go ahead and divide both sides by 2 pi. So you get T divided by 2 pi is equal to the square root of length divided by the acceleration due to gravity. All right. And so now, in order to get L by itself, we've got to multiply the square root of acceleration due to gravity to both sides. So we're going to get T times, the square root of a G divided by 2 pi is equal to the square root of L. But L still isn't by itself. We've got this pesky little square root function here. So we are going to square both sides to eliminate this square root. So eventually, we're going to have the working formula of L is equal to T squared AG divided by 4 pi squared. So now that we have our formula, we can go ahead and put our numbers in and solve for this. So L is equal to, again, 12 seconds is the period squared, multiplied by 9.81 meters per second squared, and divided by 4 pi squared. Now, if you want to put this into your calculator and solve it before you see the answer, hit pause. Otherwise, you should get an answer of 36 meters. That is your answer. Okay, again, our displacement is in meters. You can also have it in centimeters, whatever makes most sense in terms of your writing. So that means that the length of our pendulum, having known that the period is 12 seconds, and gravity is 9.81 meters per second squared, and the pendulum is attached basically to the top of the tower and basically reaches the bottom of the tower's floor. The height of the tower should be 36 meters. There, now you've done it. You have determined and solved for your tower that mysteriously appeared on your walk. Okay. Next, we're going to do, I'm not going to do this question here because you might see that one in a little bit. Okay, so going on to sample problem C. Sorry, I'm just trying to get some scrap paper here situated. All right. So, the body of a 1,275 kilogram car is supported on a frame by 4 springs. So we're dealing with a mass spring system now. Okay, 2 people riding in the car have a combined mass of 153 kilograms. When driven over a pothole in the road, the frame vibrates with a period of 0.840 seconds. So for the first few seconds of that vibration, it approximates simple harmonic motion. Find the spring constant of a single spring. So looking back at the equation, the equation for the mass spring system, we have T is equal to 2 pi, it's not in frame there, 2 pi times square root of m over k, which again is the spring constant. So our mass in total is going to be the car plus the occupants. Okay, so that's going to give us a total of, let's see, we got 1,275 plus 153. Now, one thing we have to remember is early in the problem, it said that we are dealing with a car that has 4 springs that support this weight, and we need to figure out what a single spring's values are. So you're going to take the mass of the car plus the mass of the occupants and divide that by 4 to see what how much mass is being supported by a single spring, and we get 357 kilograms. Okay, we know that T is 0.840 seconds. We are trying to find the spring constant. Okay, so we're going to take this equation and rearrange it to solve for k. And so the first thing that might make it easiest for us to do is simply get rid of this square root. So what we're going to do is we're going to square everything on here. So now we're going to have the equation of t squared is equal to 4 pi squared multiplied by m over k. So now we need to rearrange it to solve for k. So what I'm going to do is I'm basically going to swap t squared and k, and we're going to get k is equal to 4 pi squared multiplied by m over t squared. Okay? And now that we know this, we can go ahead and put in our numbers. Our mass again for a single spring that is supporting the mass is 357 kilograms. T is 0.840 seconds. Again, we have to square that. Now again, K, as we saw in section 1, has units of newtons per meter. So remember that when you give your answer. So now that we have our values in our calculator, we can go ahead and solve. So if you want to, you can wait a second. You can hit pause and solve for this yourself. And when you do, you should get an answer of 2.00 times 10 to the 4th Newton per meter. Okay? So that is a spring constant for a single spring of this car that's going to have that particular period on the frame. Okay? So again, look over this video again. Go back if you need to. Okay? With this video, your first assignment should be posted along with it. And so make sure you watch the video, take the quiz, and be on the lookout for your next homework quiz sometime probably early next week. Okay? And so that's going to be dealing with the mass spring system. Well, I hope you all thoroughly enjoyed this discussion. If you have any questions, again, feel free to contact me either through classroom or email. And stay safe, stay healthy, and I will be talking to you later. Bye-bye.